Assalamu alaikum students. Today's topic is going to be about simple harmonic motion and circular motion. Now let us see them together side by side. Now as you can see over here, this is a circular motion. The body is moving in a circular path and it has a radius r over here. Whereas we are comparing it with a mass attached to a spring system where m is attached over here and the spring is pulling it towards its mean position. If we say we are mentioning the points over here, let's call this point B, let's call this point A and this point C. Now, this point A will be the mean position of this mass attached to a spring system. This is the mean position, whereas point C and B are the extreme position. That means far from the midpoint. Now, in this case, we are comparing it to a mass attached to a circular motion. Now in this case, let's call this point C, this point A, this point B, this point A dash or A you can say, and then C again. Now we are comparing both of these motion side by side. So we are mentioning them in a form of this graph. Well, on the graph, on the x-axis, it is representing time, and on the y-axis, it is representing displacement. As the body moves from point C to point A, this was point C to point A, as you can see, the mass attached to a spring system also moved from point C to point A. And you can see on the graph, both the bodies were moving from point C at the extreme position to the mean position, which is over here from point C to point A. Now, how we have to divide this whole thing? We are dividing into 4 parts, 1, 2, 3, and 4. That means we are dividing the whole circular motion into 4 parts, like this. So this much part was covered. So out of 4, how much time was covered? Yes, t by 4. So in the first part, when the body moved from point C to point A, it has covered t by 4 time. If we want to write down in the form of radian, then we can use this formula, that theta is equal to omega t. And we want the body to move in a circular motion, we can say 2 pi divided by t into small t, where omega is equal to 2 pi. That means the distance traveled by the body, which is 2 pi, the whole circle, and in what time? The time period t. Now, if we put in the values of t by 4 in this equation, we get theta is equal to omega 2 pi divided by t, and if we put the value of t by 4, it will be t by 4. This t and this t will cancel out. 2 ones are, 2 twos are. So it will be theta is equal to pi by 2. So in radian form, this value or this time period will be pi by 2. So body is at the mean position in the case of simple harmonic motion, but it is at point A in the case of circular motion. But if we see it like this, that if we put a shadow or light over here, then its shadow will exactly be underneath this mass attached to a spring system. If the light is coming from here, then it shows that as the circular motion was moving, simultaneously the mass attached to spring system was moving along it, because its shadow was moving along the mass attached to a spring system. If we continue and the body moves now it has moved from point A to a new point, let's say point B. Now the B point is quite opposite to that of point C, as you can see over here. So it is in the opposite direction. That is why the negative sign is there. Now this is point B. And as you can see over here, it has moved from point A to point B. And in the same manner, it has moved in the case of mass attached to a spin system, it has moved from point A to point B as well. Now in this case, we have seen that what will be the value of radian at this point. Again, we have to follow this formula. Theta is equal to omega t is equal to 2 pi by t multiply. Put in the values of this t in the small t1. That means this one. So if we put in the values of small t is equal to t by 2 in this formula, let's see what happens. So t by 2, and in this way, we can cancel out this t with this t, this 2 with this 2. So only thing which is left is pi, which is 180 degree in degree form. So this point, at this point, the body has covered 180 degrees or pi radian. In the same manner, when it moves from point B in a circular motion to point A, back in the same manner, you can see the body moves from point B to point A in the case of simple harmonic motion in a mass spin system as well. And in the same way, we can say that if we shine a light on it, its shadow will be right underneath the mass attached to a spin system. And in this case, the body moves from point A graphically as well to point A from point B. So as you can see, they both are synchronized. Last, we can see as it moves from point A to point C. Now at this point, as you can see, mass attached to a spin system move from point A to point C, and over here as well, it moved from point A to point C. And in this case also, we can see that it has reached its maximum displacement from its mean position, which was shown over here, which is x naught. Now, if we want to write down in the form of radian, again, this formula. Theta is equal to omega t is equal to 2 pi by t, the time period, multiply, put in the values of this t over here. It will be t, cancel with this t, the value of radian will be 2 pi. So it has moved a whole circle, that is why the 2 pi radian is given at point t. Now, if we convert this in a graph form, we can see that the whole graph was represented by a blue line, that it moves from extreme position, moved down to the mean position, then moved to the extreme position again, back to the mean position, and back to the extreme position again to this original position. So these are the qualities of a mass attached to a spin system as well as simple harmonic motion. That is, it is moving to and fro. Now in this case, we have seen that a body moves to and fro about a mean position just like in the case of mass attached to a spin system. But it was happening on a circular motion as well. Now, if we are considering a vertical system, let's see what happens that. Now, in this case, we have a mass attached to a spin system, but it is hung now vertically. The distance from A to C is same that as the uh, x naught, which is the maximum displacement from the mean position, and that much displacement is same as AB also. And that distance is equal to the radius of the circle, which will be shown later on. As we move, let's say, and we focus on the graph as well. Now we are focused on this circle now, because we have already mentioned this circle for the horizontal part. Now, as we move along the vertical component of the mass attached to a spin system, it moves from point A to point C. Let's see what happens. So it moves from point A to point C. That means it displaces from point A to point C. In the same method, you can see it moves from point A to point C in the circular motion as well. Now, as we light up this space, the shadow of this mass attached to a circular motion will form at the right point as where the mass attached to the spin system was. Now, in the same manner, if it moves from one position to another, we are going to note down the radian part again. Theta is equal to omega t is equal to. Now, how can we write this down? 2 pi divided by t Now, in this case, what was the displacement? What was the time period? It was t by 4. Now, in this case, if we put t by 4 in the value of t, this t cancels out, the value of this will be equal to, or this 2 and this 4 will cancel out, the value of theta will be equal to pi by 2 or 90 degrees. Now, what is the function at which the value of 90 or pi by 2 is maximum and the value for 0, or you can say 0 degrees or 0 radian, is minimum? Yes, that is a function of mathematics, that is sine theta. At angle sine, the sine 90 is maximum value of sine and sine 0 is minimum at sine. In a similar method, which value of it will be minimum? Let's reverse it all. If I want to reverse this as a eraser, I just remove this part. If I just reverse it, now I want a function of mathematics in which where the sign was maximum and minimum, so it was 90 and 0. But if I want minimum at 90 and maximum at 0 degrees, that is also a function of mathematics which is known as cos theta. That means cos theta is maximum at 0 degrees and minimum at 90 degrees. Now, what we have seen over here, this vertical part, as we can see over here, the mass attached to a spring system is following the sine theta, and the mass attached to a spring system along horizontal part was following horizontal or cos theta. Now, as it moves from point C, the maximum point over here, to point A back, we'll see that the whole body moved from point C to the midpoint, as mass attached to the spring system also moved to the mean position, and circular motion moved along the same path. That means it reaches point A. In the same method, we can write down that as it moves from point A to point B, over here, if we light a shine or light over here, the shadow of it will fall upon the mass attached to the spring system. That means it is following the same procedure, that it moves from point 0 to a maximum displacement from mean position, but in opposite direction, which is x naught, negative. This is also x naught. But I showed you that this distance A part and this distance B, the distance AB is equal to the radius of the circle. So in this case, we can say the both circular motion and simple harmonic motion, mass attached to a spring system, are moving synchronized. Now in this case, let's move forward. It moved from point B back to point A. Now from graph we can see, the graph part, that it has moved from point A, right over here, to its extreme position, oh sorry, its mean position. We are following this mass. So it moved from its extreme position right from here to point at the mean position, which is point A. And in this same method, we can say that we have reached from point B to point A. Now, if we want to memorize that how these two bodies were moving vertically as well as horizontally, we can first of all draw a graph of mass attached to a spring system and circular motion vertically. We see a graph of sine theta. That means it is 0 at an angle of 0. It is maximum at 90 degree or pi by 2. Now, if we want to see them together, both the horizontal and vertical mass attached to a spring system, to compare it with the circular motion, let's see what happens then. We are drawing both the graphs of the red one is showing the sine theta, whereas the blue one is showing the cos theta or the vertical component. The blue one is for the horizontal part H, and the red one is for the vertical part, which is sine. Let's see how it goes. As you can see, the mass in the horizontal part moved from point C to point A, It also moved from point C to point A. It also moved from point A to point C over here. As you can see in the graph as well, it moved in the horizontal case from point C to point A, and in the case of vertical, it moved from point A to point C. Let's continue. It moved from point C to point A. Now, in the case of vertical, it moved from point C to point A. As you can see in the red, it moved from point C to point A over here. And in the case of horizontal, it moved from point A to point C, right over here. Let's continue at this point. After this point, let's continue. What will happen? We'll see that it will move from point A to point B. Let's see. This is point B and this is point B. So it moved from point A to point B, which is the horizontal part as well, from point B to point A. The blue line, point B, which is the maximum, to point A again. And let's look at the vertical part. It moved from point A to point B right over here, which is the extreme part. Last part, let's clear this out. Yes, the last part, when it moves from here to here, let's say from point A to point, sorry, this was point B, and for vertical part, and this was point A. Now, if it moves from here to here, let's see this simultaneously, it will move like this. Now, as you can see, it moves back to its mean position. It moves back to its extreme position, and both of them are showing the same graph. That means both circular motion and mass attached to a spring system, which was showing simple harmonic motion, was synchronized and following the same concept. That means circular motion is showing simple harmonic motion. And this is what we have found out today, that even if we take the horizontal part, even if we take the vertical part, we can show that circular motion will show a simple harmonic motion. I hope you enjoyed today's lesson, because I really did. Inshallah, we'll meet again. Allah.